So this is a simulation of distortion. We have distortion here modeled in a camera, and this point here is where the camera is located in physical space. This is typically called a frustum. This is a small synthetic image where each of these points would be a pixel in the image. So right now we have zero distortion, and because of that you can see the rays extending out of the camera all have the same angle between them, both in the horizontal and in the vertical of the image. So as we change the distortion, you will see that these will start to bend, and it's probably a little easier to see if you look at the image itself. So these lines that were once straight now have a curve to them. As the single parameter of the distortion increases above zero, you'll see that the line becomes curved and that the points move farther in towards the center. You'll see that the points in the middle exhibit very little distortion, whereas the points on the outside of the image exhibit the largest amount of distortion. So then if we go back to the beginning where the distortion is zero, you again see the points where they ought to be with a constant angle between them. And as we go into the negative parameter of distortion, you'll see that the points move from where they are outward, and again that there is this line which exists in space is no longer straight. You have a curvature. It's now in the opposite direction, and that curvature happens both in the horizontal and in the vertical. So as we go a little farther out, you'll see that the distortion and the curvature gets much worse. So this is what distortion looks like in a real image. This is just a standard piece of computer paper, 8.5 by 11, imaged by a Samsung Galaxy tablet. What you notice here is this blue line here is a line that I've marked out. I've marked the edges of the pixel of the sheet in a straight line, and that straight line should line up with this edge, but because there is distortion, in this case enough to offset this line by about 8.5 pixels, it doesn't line up, and we can use this fact actually to correct for the distortion using an algorithm. So you may wonder, why do we care about distortion? This is a little synthetic experiment here to demonstrate why you might care about distortion if you're trying to localize a camera for augmented reality or special effects. What you see here is a representation of a camera in space. This larger green, red, and blue line represents a camera. This blue line being the direction that the camera is facing, and this blue border here is where the image would be, and it's imaging this set of points down here in the corner. And now these images of these points are being distorted before they're put into an algorithm to solve for the position of the camera, called a perspective endpoint algorithm. And the result, because the input to this is slightly distorted, is about a 5% error in the actual position of the camera, and about a 3-degree error in the angle that we have localized the camera to be in. And where this would matter is if you were trying to put a three-dimensional thing into a two-dimensional scene and put it into the image. This shows what's called a reprojection. These blue circles are where the reprojected information should actually be, and these little green X's are where they are positioned because we have a false reconstruction of where the camera actually is. So what basically this amounts to is that you're going to have misaligned images and weird artifacts in your scene if you are, positioning the camera poorly. Now, if we had that object filling up the entire screen, those errors would probably be a lot less. But all the same, distortion causes error in figuring out where a camera is and being able to produce a scene from that. So if we want to find the corrective parameter for removing the distortion so that we have better three-dimensional reconstruction and augmented reality, it would be nice if we can get that parameter from the environment itself based on the fact that a line should be straight. There are, of course, ways to do it using calibration targets, but that requires you to have a specialized target to do so. So again, this scene is of that standard computer paper with the warped edges, and I'm going to show a demonstration of this algorithm. It's an iterative algorithm that takes these input x's, that's the edge that is curved that we know to be straight, and it solves at each step to align the edge to something which actually is straight. And you can see at each iteration it slowly forms this straight line based on a guess of that input parameter. Up to this point, we have assumed that the lines were no, so I'm going to cover a little bit now about the algorithm on how to extract subpixel accurate lines from an image. So what you're looking at here is, again, that standard piece of computer paper, and these colored marks here are little line segments which I've extracted using an algorithm for subpixel accurate edge detection. So this algorithm works using the gradient of the image as the input extraction mechanism, and I'll show this. What you're seeing here is a false color image of the gradient in the image. Essentially, gradient's pretty high around anything that's an edge. So this false color blue is a low value, and then it goes up towards red, green being somewhere in between. So you can see that there's a pretty high gradient here along those edges. Again, we'll go back to the regular image and you can see that. And from that gradient, we can also extract the orientation of the edge using the covariance. And again, this is a false color, red being high, blue being low. In this case, it's mapped between 0 and 180 degrees. So these vertical lines look blue and red because the orientation can go in either direction, left or right, 0 and 180 basically being the same. It's a little more obvious with these horizontal lines. This green in between 0 and 180 is about 90, so this is indicating that the line is essentially horizontal. These line segments are then constructed by walking along the gradient for a set of maximas that have met threshold. And you can see that there's also other lines in here that meet that criteria, but they're not appropriate for computing distortion. You need the lines to actually be physically straight. So we're going to just select a few of them to compute our distortion from. And I'm going to go ahead and show the subpixel accuracy of these in this little sub-window here. So this little sub-window shows the lines along the detected line here, and you can see they fall in this gradient, which is a 10-fold zoom, and basically along the same place in what's considered the subpixel line, to within a fairly accurate amount. So we'll continue to select a few more of these lines. So, and from that we compute a distortion factor of roughly 0.5, which I know to be fairly close from a standard chessboard calibration. What you're looking at here is these red lines are where the lines were, or where the points were originally in the image, and then the distortion factor made them straight and expanded the image in order to fit the straight lines to that distortion parameter. So this is the corrected image. We're going to run the straight line test on it like we did in the distorted image to see that the line is indeed much straighter. So you can see already this blue line basically falls along that edge. If we zoom in, it's going to be within my ability to choose where this line is, but looks like it's about a pixel. And before it was about 8.5, so it's a fairly substantial improvement, and it looks as though we have computed distortion correctly.